Hi, this lesson is about rates of change in the natural sciences. So, we're going to talk about rates of change in physics, chemistry, biology, economics, and then do some examples of each. So, some examples in physics would be regarding displacement, velocity, and acceleration. So, we know that um, the average rate of change of one dependent variable with respect to an independent variable would is just the same as a slope calculation. So if we call s of t the position or displacement function of a particle moving in a straight line, where t is time, then the average velocity would be the change in s divided by the change in t over a particular range of time. And yet the instantaneous rate of velocity or the instantaneous velocity would be your derivative of s at a particular time t. The average um, the average acceleration would be the change in velocity over the change in time, and your instantaneous rate of acceleration would be the derivative of the velocity at a particular time t. So what that means is that the acceleration, the instantaneous acceleration, would be the second derivative um, of your displacement function. Because remember, the first derivative is your velocity function. The total distance traveled over some time period would be the absolute value of S of t. In chemistry, we can talk about the concentration of a chemical. So if C of t is the concentration of a chemical, then the average rate of reaction over some time period would be the change in C over the change in t. Again, where t is time. And the instantaneous rate of reaction or the instantaneous reaction of a chemical would be the derivative of C with respect to t. So this is C prime of t or dc dt. In biology, we can consider the number of individuals or animals, species in a particular population of animals, plants, could be bacteria. So it's some sort of number of individual items in a population. The average rate of growth over a particular time period from time 1 to time 2 would be the change in n, if n is your function of time, over change in t. So it's again just a slope calculation. And your instantaneous rate of growth, there's a little typo here, would be the derivative of n with respect to t. In economics, if we let C of X be the total cost that a company incurs to produce X units of a commodity, you can compute the average rate of change in the cost by doing the change in cost divided by the change in the number of commodities. Remember, X is the number of units of the commodity. So again, change in C over change in X is just a slope calculation. The change in the dependent variable divided by the change in the independent variable. But the instantaneous cost would be the derivative of C. So C prime of X is the derivative of C with respect to X. The instantaneous rate of cost in business terms is also called the marginal cost. So that's the cost for making a particular commodity. How much is it to make the 20th commodity or the 2 millionth commodity? That would be your instantaneous rate of cost. So let's do a couple of examples. So example 1 says a company makes computer chips from square wafers of silicone. It wants to keep the side length of a wafer very close to 11 millimeters. And it wants to know how the area, A of X, of a wafer changes when the side of length x changes. All right, so we know that we're dealing with a square, and if the length is side x, then the formula that we're considering here is a of x is equal to x squared, which is x times x. That's the area of a square. If we take the derivative of the area with respect to x, you get that a prime of x is equal to 2x. But now we want to figure out what is that change in the area when your length of the side is 22. So at x equal to 11, a prime would be 2 times 11. And so the rate of change of the area would be 22 millimeters per second for every millimeter. So when your length is 11 millimeters, you expect your average to change at 22 millimeters squared per millimeter. So the next one is a three-dimensional shape. It's a spherical balloon is being inflated. Find the rate of increase of the surface area with respect to the radius r, where the radius is 3 feet. Okay, so the formula for the surface area of a sphere is S equal to 4 pi r squared. So this is a function of radius. So the derivative, S prime, would be 8 pi r. You just do power rule. The pi is a coefficient, so it's just 2 times 4 times pi, so we get 8 pi r. Now we know that the radius is 3. And we want to find the rate of increase of the surface area. So we're solving for S prime when R is 3. So you plug that in and you get that the surface area when the radius is 3 feet is 24 pi feet squared per feet. So let's move on. This is a physics example. We have, if a ball is given a push so that it has an initial velocity of 5 meters per second down a certain inclined plane, then the distance it has rolled after t seconds is given by the equation S of t equal to 5t plus 3t squared. So part A asks us to find the velocity at 2 seconds, and part B asks how long does it take for the velocity to reach 45 meters per second. All right, so the first thing we need to do is find the velocity, and then we will substitute 2 in for t. So since we want to know the velocity at a particular moment of time, we're looking for an instantaneous velocity, which is a derivative. So the derivative of displacement is velocity. We use power rule, and we get 5 plus 16. Now we're ready to plug in 2 for t. And so the velocity at 2 seconds is 5 plus 6 times 2. So we have a velocity of 17 meters per second. Part B wants to know when does it reach 45 meters per second. So that means we take our velocity function and set it equal to 45. This is now a linear equation. So we subtract 5 from both sides and we get 6t equals 40. Divide by 6 and reduce it, and we get that your time is 20 over 3. And so converted to a mixed number, the ball reaches 45 meters per second at 6 2/3 seconds. Okay, here's another. The position of a particle is given by S of t equal to t cubed minus 6t squared plus 9t. Where S of t is measured in meters and t is measured in seconds. Part A says to find the velocity function at time t. And part B asks us to determine when the particle is at rest. So for part A, I again have to find the derivative of my displacement function. So if you use your power rule, you get 3t squared minus 12t plus 9. Then to answer the second part, when is the particle at rest? Well, the particle is at rest when our velocity is equal to 0. So we take the derivative that we found in part A and we set it equal to 0. So this is a quadratic equation. and it is factorable. So if we factor out a 3 first, you're left with 3 times t squared minus 4t plus 3. And then we factor this trinomial, so we get 3 times t minus 3 times t minus 1. And we get that the particle is at rest at 1 second and at 3 seconds. Okay, here's another. A particle moves according to a law of motion, which is s of t equal to t cubed minus 9t squared plus 24t, when your time is greater than or equal to 0, and time is measured in seconds, and s of t is in feet. Part A says to find the acceleration at t equal to 5, and part B asks us to find when the particle is speeding up and when it is slowing down over the interval from 0 to 7. Okay, so let's do part A first. To determine the acceleration, I need to take the second derivative of my displacement function. So first thing is find your velocity function. The derivative of s of t is velocity. So if we do power rule, we get v of t is 3t squared minus 18t plus 24. Then acceleration is the derivative of velocity. So acceleration, again, take your derivative rules here, and you get 6t minus 18 as your acceleration function. But now we can plug in 5. And so your acceleration at 5 seconds is 6 times 5 minus 18. So we have an acceleration of 12 feet per second squared at 5 seconds. For part B, when is the particle speeding up and when it's slowing down? All right, so we need to figure out, well, when is it just 0? When is your acceleration 0? So we can then answer that question. So we take our acceleration function here and set it equal to 0. So it's linear. You add 18 and then divide by 6, and you get that it is acceleration is equal to 0 when t is equal to 3. So if we set up a little line, number line here to help keep us organized, we know that our time interval is from 0 to 7, and that at 3, acceleration is equal to 0. So if we take a test point, something between 0 and 3, let's say t equal to 1, and we plug it into acceleration, that will give me a negative result. Your acceleration is negative between 0 and 3. And if you take a test point between 3 and 7, you can pick anything you want. So let's say 5, and you plug that in your acceleration function, that will give you a positive result. So the particle is slowing down when your acceleration is negative. So it's slowing down on the interval from 0 to 3, but your particle is speeding up when your acceleration is positive, and it is positive on the interval from 3 to 7. Okay, so that's it for that lesson. Give the homework a try. Good luck.